Good afternoon, everyone. I am Giorgina Delfin, along with my group mates Lydith Mae Bilog and Jamhyca Lee Alaba, and welcome to our comprehensive exploration of thermodynamics focusing specifically on spontaneous reactions and gives free energy. In this presentation, we will break down complex concepts into easily understandable terms, allowing you to grasp the fundamental principles underlying energy changes in chemical systems. So, what really are thermodynamics? Thermodynamics is a big word, but don't let it intimidate you. It's essentially the study of how energy moves and changes from one thing to another. Imagine energy as little workers constantly moving around, getting things done. When we talk about thermo, we're talking about heat, like when you feel warmth from the sun or a cozy blanket. And dynamics is just a fancy way of saying movement, like when you see a car zooming down the street or a ball bouncing around. So when we put it together, thermodynamics is all about understanding how heat and movement work together. It's like figuring out the distance between different forms of energy. Think of it as a big puzzle where we're trying to understand how everything fits together and how we can use that knowledge to make things better. Whether it's making engines more efficient or keeping our homes warm in the winter, thermodynamics is the key to unlocking the secrets of energy flow. Now let's proceed to the first lesson of this chapter, which is the spontaneous reaction. So, what really are spontaneous reactions? In simple terms, a spontaneous reaction is one that happens naturally without needing any outside force to make it occur. Imagine a ball rolling down a hill on its own. It moves because it naturally wants to go in that direction, just like a spontaneous reaction occurs because it naturally favors the formation of products. So, what exactly makes a reaction spontaneous? It's all about the balance between the reactants and products. If the products are more stable and happier than the reactants, the reaction will tend to move towards forming those products. Think of it like rearranging furniture in a room to make it more comfortable. The reaction happens because it energetically favorable for the system to reach that more stable state. Now, even if a reaction is spontaneous, it doesn't mean it happens instantly. Some spontaneous reactions can be slow, like rusting of irons, but they can still occur over time because they are driven by the natural tendency of the system to achieve a more stable state. So, in essence, a spontaneous reaction is like a natural process that unfolds on its own, guided by the inherent properties of the reactants and products involved. Now let's explore the factors that determine whether a reaction is spontaneous or not. The first one is the enthalpy change. Enthalpy is a measure of the heat energy in a system. When a reaction absorbs heat from its surrounding, it's endothermic, meaning delta H is positive. On the other hand, if a reaction releases heat to its surroundings, it's exothermic, meaning delta H is negative. Spontaneous reactions can occur whether they are exothermic or endothermic, but the sign of delta H provides insight into the direction of the reaction. The second one is the entropy change. Entropy is a measure of the disorder or randomness in a system. When the entropy increases, it means the system becomes more disordered, and when it decreases, the system becomes more ordered. Spontaneous reactions tend to occur when there's an increase in entropy or entropy is positive, as nature tends to move towards more disorder. However, some non-spontaneous reactions can occur if the entropy change is offset by other factors. At equilibrium, where the forward and reverse reactions occur at the same rate, the entropy change is zero, indicating a state of maximum disorder. The last one is the temperature. Temperature plays a crucial role in determining whether a reaction is spontaneous. Increasing the temperature can make a non-spontaneous reaction become spontaneous by providing the necessary energy to overcome activation barriers. Conversely, decreasing the temperature can make a spontaneous reaction become non-spontaneous by reducing the kinetic energy of the particles and slowing down the reaction rate. In short, the spontaneity of a reaction is influenced by the enthalpy change, entropy change, and temperature. Understanding these factors helps predict whether a reaction will occur naturally or if external intervention is required to drive it forward. Moving on to spontaneous change. Spontaneous change is a fundamental concept in nature describing processes that occur without any external assistance. This phenomena can manifest at varying speeds, from lightning fast to remarkably slow, illustrating the diverse ways in which nature operates. For instance, consider the biochemical reaction that occurs when you accidentally touch something hot. Your body's immediate response to the heat, such as pulling away to avoid injury, exemplifies a rapid and instinctive spontaneous process. This example highlights how our biological systems are finely tuned to react swiftly to potential threats, showcasing the efficacy of spontaneous reactions in ensuring our survival and well being. Conversely, the gradual erosion of a mountain serves as a testament to the slow yet persistent nature of spontaneous change. Over thousands of years, natural forces like wind, water, and weathering gradually wear down the mountain's surface, reshaping its contours over time. While the observable changes may occur at a glacial phase, the underlying processes driving this erosion are spontaneous, driven by the inherent tendencies of geological systems. This example underscores how even the most monumental transformations in nature can stem from the cumulative effects of incremental spontaneous changes occurring over vast time scales. Now let's explore some examples of spontaneous processes to deepen our understanding of spontaneity. The first one is the heat flow. Heat naturally flows from a hotter object to a cooler one due to the second law of thermodynamics, which states that heat spontaneously moves from higher to lower temperatures. The reverse process, where heat flows from a cooler object to a hotter one, doesn't occur spontaneously because it goes against this natural tendency. The next one is the gas dispersion. In a container, a gas tends to uniformly fill the available space because of its entropy and random motion of particles. Spontaneously, it doesn't collect at one side of the container as this would decrease the system's entropy. Now let's explore some examples of spontaneous processes to deepen our understanding of spontaneity. The first one is the heat flow. Heat naturally flows from a hotter object to a cooler one due to the second law of thermodynamics, which states that heat spontaneously moves from higher to lower temperatures. The reverse process, where heat flows from a cooler object to a hotter one, doesn't occur spontaneously because it goes against this natural tendency. The second one is the gas dispersion. In a container, a gas tends to uniformly fill the available space because of its high entropy and random motion of particles. Spontaneously, it doesn't collect at one side of the container as this would decrease the system's entropy. The third one is the rolling marble. When a marble rolls down an inclined plane, it does so due to the force of gravity. However, it doesn't spontaneously roll back up the incline because that would require an input of energy against gravity, which doesn't occur naturally. The fourth one is the combustion of wood. Wood burns spontaneously in an exothermic reaction because it releases heat and forms carbon dioxide and water. However, heating carbon dioxide and water together doesn't spontaneously produce wood because it requires an external energy source to reverse the reaction. And lastly, the rusting of steel. When steel is exposed to air and moisture, it rusts spontaneously due to oxidation reactions. However, the reverse process where rust spontaneously changes back to iron metal and oxygen gas doesn't occur without external intervention because it would require a reduction process. In summary, these examples illustrate the principle of spontaneity and highlight the natural tendencies of physical and chemical processes to move towards states of lower energy or higher entropy without external assistance. The next one is, what thermodynamic principle can provide an explanation as to why the processes mentioned occur in one direction but never in the reverse? The thermodynamic principle that can provide an explanation to this is the second law of thermodynamics. This law states that the entropy of an isolated system tends to increase over time, leading to a natural progression toward states of higher entropy or disorder. While early scientists initially associated spontaneity with exothermic reactions, it became evident that this factor alone does not fully explain spontaneity. Although many spontaneous processes are indeed exothermic, other factors such as entropy changes also play crucial roles. Spontaneous processes tend to be those that increase the entropy of the system, promoting disorder or randomness. Therefore, the second law of thermodynamics provides a more comprehensive explanation for the directionality of spontaneous processes. It emphasizes the tendency of natural systems to move toward states of higher entropy, driving spontaneous processes in one direction while inhibiting their occurrence in the reverse direction. Contrary to common belief, spontaneous reactions can also occur in thermodynamic processes where energy is absorbed from the surroundings. A classic example of this is the melting of ice. When ice absorbs heat energy from its surroundings, it transitions from a solid to a liquid state, even though this process requires an input of energy. This spontaneous change occurs because the increase in entropy associated with the transition to a more disordered liquid state outweighs the energy input required for the phase change. Another example of a spontaneous endothermic process is the dissolution of salts in water. When certain salts, such as sodium chloride or table salt, dissolve in water, they absorb heat from the surroundings, making the solution colder. Despite the energy input needed for the dissolution process, it occurs spontaneously because it leads to an increase in the disorder of the system as the salt ions become dispersed throughout the solvent. Therefore, this examples illustrates that spontaneity is not solely determined by exothermicity but also by changes in entropy that favor increased disorder or randomness in the system. Moving on to our next topic, which is the entropy. Entropy, denoted by the symbol S, is a fundamental concept that plays a crucial role in all spontaneous processes. It can be thought of as a measure of molecular randomness or disorder within a system. In simpler terms, entropy tells us how dispersed or spread out the particles are within a system. For example, a gas has a higher entropy than a liquid because its particles are more randomly distributed and have greater freedom of movement. Similarly, a solid has lower entropy than a liquid because its particles are more closely packed and have less freedom to move around. Entropy is a driving force behind spontaneous processes because nature tends to favor states of higher entropy. This means that spontaneous processes often lead to an increase in the disorder or randomness of the system. For instance, when a solid dissolves in a solvent, the resulting solution has higher entropy because the particles are more dispersed than they were in the solid state. Therefore, understanding entropy allows us to predict the directionality of spontaneous processes and provides insight into the natural tendencies of physical and chemical systems. First, entropy for a given substance, the entropy of gas is greater than the entropy of the liquid or solid. When a substance transitions from a solid or liquid state to a gas, its entropy typically increases. This is because in a gas phase, the particles have greater freedom of movement compared to a more structured solid or liquid phase, just like what I've said earlier. To illustrate this concept, let's consider water. In its solid state, which is the ice, water molecules are tightly packed in a crystalline structure with limited freedom of movement. As it transitions to a liquid state, the molecules gain more freedom to move around, resulting to an increase in entropy. Finally, when water vaporizes into a gas, the molecules have even greater freedom of movement as they disperse throughout the space, contributing to a further increase in entropy. Thus, the entropy of water in its gas phase is greater than it is in a liquid or solid phases. This trend generally holds true for most substances undergoing phase transitions. This ends my part in the reporting. I will now give the floor to Ms. Lydith Mae Bilog to continue the discussion.
Number 2. Entropy often increases in chemical reactions in which the total number of product molecules is greater than the total number of reactant molecules. It means that when the total number of product molecules in a chemical reaction exceeds the total number of reactant molecules, the products are typically more complex or have a greater freedom of movement than the reactants. The increase in complexity or freedom usually results in an increase in disorder or randomness, which is reflected in the increase in entropy. Simply put, the reaction causes the system to become more chaotic or disordered. Next, number 3. Entropy increases when a substance is divided into parts. For instance, when an ionic compound like sodium chloride dissolves in water. When sodium chloride or salt dissolves in water, its tiny particles spread out, surrounded by water molecules. This spreading out makes things more random or disordered, which we call entropy. So in simpler terms, when salt dissolves, things get messier, making the system more chaotic. Sa picture, makita nato si sodium chloride or salt na tightly packed pa siya. Pero if i-add na to si H2O or si water, ang molecule sa sodium chloride nag-spread out or nagkatag, which means ang entropy niya nag-increase. Next page, number 4. Entropy tends to increase when temperature increases. As the temperature rises, the molecules move faster, which increases disorder. Entropy tends to rise as temperature rises. As the temperature rises, molecules move faster, resulting in more disorder. Makita nato sa figure A na ang molecule sa sulod sa beaker is dili kayo scattered. Then sa figure B and C, habang naga-increase ang temperature, naga-move faster ang molecules, which means naga-increase iyang randomness or disorder. Next, to calculate the change in entropy in the universe, we should focus on the change in entropy in the system. Suppose the system is represented by H2G plus Cl2G, then 2HClG. The standard entropy of the reaction can be solved by delta of the reaction is equal to the sum of entropy of product minus the sum of entropy of the reactants. Next is revisiting enthalpy. The enthalpy, or H, of a substance represents the energy of that substance. Enthalpy changes are summarized as So enthalpy in chemistry is like a measure of the total heat energy within a system, considering both its internal energy and energy associated with its pressure and volume. It's super important for figuring out how heat moves during chemical reactions and when substances change from one phase to another, like from a solid to a liquid. Number 1, change in enthalpy reaction is equal to the change in enthalpy products minus change in enthalpy of the reactants. Number 2, negative change in enthalpy. Means that the reaction is exothermic. Again, an exothermic reaction is a chemical reaction that releases heat energy to its surroundings. During an exothermic reaction, the products have lower energy than the reactants, resulting in a negative change in enthalpy. Common example includes combustion reactions such as burning fuels like wood or methane, where heat is produced as a byproduct. Then, positive change in enthalpy means that the reaction is endothermic. An endothermic reaction is a chemical reaction that absorbs heat energy from its surrounding. During an endothermic reaction, the products have higher energy than the reactants, resulting in a positive change in enthalpy. Common examples include processes like photosynthesis in plants, where energy from sunlight is absorbed to convert carbon dioxide or water into glucose and oxygen. Number 3, the standard enthalpy change is the heat transferred in the reaction with reactants and products in their standard states. So change in enthalpy reaction is equal to change in enthalpy products minus change in enthalpy reactants. Next is number 4. The enthalpy change is directly proportional to the amount of reactants and products involved. The formula is the change in heat in a reaction is equal to the difference in heat of the products and reactants. Next page. Entropy and second law of thermodynamics. A process is said to be spontaneous if it results in an increase in disorder. This principle can be stated in terms of entropy. As in any spontaneous process, there is always an increase in the entropy of the universe. This statement is a reflection of the second law of thermodynamics, which states that in any spontaneous process, the total entropy of a closed system and its surrounding always increases. It means that natural process tends to move towards the state of greater disorder or randomness. This is the second law of thermodynamics. The second law of thermodynamics tells us that the entropy of the universe is increasing. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. In simpler terms, it means that in any natural process, the overall disorder or randomness tends to increase, or at best, stays the same, but it never decreases on its own. The change in entropy in universe is equal to the change in entropy in the system, plus the change in entropy in the surrounding. If the change in entropy in the universe is greater than 0, it is spontaneous. And if the change of entropy in the universe is less than 0, it is non-spontaneous. And if the change in entropy in the universe is equal to 0, the reaction is at equilibrium. So, enthalpy and entropy. For any chemical reaction, heat is released or absorbed, and in every reaction, entropy either increases or decreases. How do these factors influence the spontaneity of a reaction? So, entropy measures disorder or randomness. Spontaneous reactions tend to increase entropy. Enthalpy measures heat energy. Exothermic reactions release heat and are typically spontaneous, while endothermic reaction absorbs heat and may be spontaneous if entropy increases enough to offset the energy input. The spontaneity determined by the balance between the change in enthalpy and the change in entropy. So, spontaneity depends on both entropy and enthalpy changes in a reaction alongside with temperature. Next page is the table 6.1, the effects of changes in heat content and entropy on reaction spontaneity. So in case 1, the heat is negative or exothermic. The enthalpy, enthalpy is positive or more disorder in products than in reactants. The result will be the spontaneous at all temperature. When both the change in enthalpy is negative and the change in entropy is positive, it's highly likely that the reaction will be spontaneous, particularly if the decrease in enthalpy dominates over the increase in entropy. This combination suggests that the system releases heat and becomes more disordered, both of which drive the reaction towards spontaneity. In case 2, the change in enthalpy is positive and the change in entropy is positive, which will result to the spontaneous at high temperatures where the change in entropy offsets unfavorable to the change of enthalpy. When the change in enthalpy is positive and the change of entropy is positive, the spontaneity of the reaction depends on the balance between these factors and the temperature. In some cases, the increase in entropy may dominate, allowing the reaction to proceed spontaneously despite the energy input. However, at lower temperatures, the positive enthalpy change may outweigh the positive entropy change, making the reaction non-spontaneous. Overall, whether the reaction is spontaneous or not depends on the specific value of the change in enthalpy and the change of entropy, and the temperature as well as the relative magnitude of these factors. Next is the case 3. When the change in enthalpy is negative and the change of entropy is negative as well, it will result to the spontaneous at low temperature where the change in enthalpy offsets unfavorable to the change in entropy. When the change of enthalpy is negative and the change of entropy is negative, the spontaneity of the reaction depends on the balance between these two factors and the temperature. Even though the reaction releases heat, the decrease in disorder tends to oppose spontaneity. However, under certain conditions, such as low temperatures, or if the enthalpy decrease is significant compared to the entropy decrease, the reaction might still be spontaneous. In summary, whether the reaction is spontaneous or not depends on the specific value of the change in enthalpy and the change of entropy, and the temperature, the relative magnitude, and these factors. Next is the case 4. When enthalpy is positive and the change in entropy is negative, which will result to non-spontaneous at any temperature. When the change in enthalpy is positive and the change in entropy is negative, the spontaneity of the reaction is less likely. Both factors contribute to a less favorable conditions for spontaneity. The energy input required by the endothermic reaction and the decrease in disorder tend to oppose the spontaneity of the reaction. Next slide. Covalent bond example. So notice that the change in entropy is directly related to a quantity of heat, Q, and inversely related to the Kelvin temperature, T. So a covalent bond forms when two atoms share electron pairs to achieve stability by filling their outer electron shell. It's common in non-metals but can occur between a metal and non-metal. Because the unit used for Q is joules and the unit used for temperature is Kelvin raised to -1, the unit of entropy change is joules over Kelvin. Next slide. To understand better, we will watch a video on how to calculate standard entropy change.
In this video, I'm going to run through how to calculate the standard entropy change for a reaction. And so we're going to look at a worked example to do this. And the question is, what is the entropy change when hydrogen peroxide decomposes into water and oxygen? And when we do the entropy change calculations, the first step is always to have a balanced equation with state symbols. The state symbols are very important because the entropy values are different depending on what state your substance is. So make sure you always include those. So we've got hydrogen peroxide, which is simply water with an extra oxygen. So that's H2O2 in the liquid state. We are told that that's decomposing into water and oxygen. So we can complete the equation and have water plus oxygen. Water, of course, the liquid. And then we've got oxygen in the gas state. So we've got our equation there. It's not balanced though. On the left-hand side, 2 oxygens, and on the right, we've got 3 oxygens. So we need to balance that, and it balances very simply just by adding those 2 2's as shown. So we've now got a balanced symbol equation with all of the state symbols. So that's the first step done. The second step is often missed out, but it's quite useful. You want to predict the sign of the entropy change. So you look at the equation and you work out, are you expecting a decrease in entropy, so a negative delta S, or are you expecting an increase in entropy? So that would be a positive value of delta S. And when we look at the state symbols, it's quite easy to work out. So on the left-hand side, we've got a liquid, which has the particles looking like that. And then we're having a liquid, and then we're having a gas. The gas has much higher entropy, much more disordered, and so we're seeing an increase in disorder. An increase in disorder means a positive change in entropy. So therefore, we've got a delta S greater than 0, implying an increase in disorder in the system. So if you get a negative value, it means you've done something wrong. If you get a positive value, then you've got some more confidence in your answer and you're less likely to have made a silly mistake. Step 3, you need to look up values in the data book and take account of those balancing numbers. So I've put a link in the description below to a table that's got a lot of the values that are used in most calculations, and you can see where I actually got these numbers from. So if you look up the S value, the entropy value for hydrogen peroxide, you will get 110 joules per kilogram per mole. Pay attention to this because it's joules and that often causes problems. And because we've got 2 moles, you have to multiply that by 2. We look up the value for water in the liquid state. Pay attention to those state symbols or you will get it wrong. And again, we've got a balancing number of a 2, so we've got 2 times that. For oxygen, we can look up the number and there's no balancing number in front of it, so we just take the number from the data tables. So that's step 3 completed. We've got all of the values that we need. In step 4, we're actually finding the change. So we're using the equation that says that the entropy change is the sum of the entropy of all of the products. So these are the products. So this plus this minus the sum of the entropies of all of the reactants. And all we have to do is substitute in. So I've replaced this expression here with this plus this for the products. And then I'm subtracting the reactants. Be very careful when you put this into a calculator because signs can go a little bit wrong. And when we do that calculation, we get the value as shown. It's coming out as a positive number, which is what we expect. And so we have now calculated the entropy change for a reaction. I hope this video was helpful to you. If it was helpful, please like and subscribe below. And finally, thank you very much for watching.
That's all for my part. Next, my groupmate Jamhyca Alaba will continue to report the lesson 2.
Now, we have here the lesson 2, which is the Gibbs free energy. So, Gibbs free energy, denoted by the symbol of capital letter G, is a concept in thermodynamics that represents the maximum amount of useful work that can be extracted from a closed system at constant temperature and pressure. In simple terms, Gibbs free energy tells us whether a chemical reaction will occur spontaneously or not under certain conditions. Gibbs free energy is affected by enthalpy change and entropy change. For a process at constant temperature and pressure, the change in Gibbs free energy, denoted by the symbol of delta G, is related to the change in enthalpy, denoted by the symbol of delta H, the change in entropy, denoted by the symbol of delta S, and the temperature, denoted by capital letter T, by the equation Gibbs free energy is equivalent to enthalpy minus the temperature multiplied to the entropy. If Gibbs free energy is negative, the process is spontaneous in the forward direction, meaning the reaction will occur without needing external intervention. If the Gibbs free energy is positive, the process is non spontaneous under the given conditions. If Gibbs free energy is zero, the system is at equilibrium, meaning there is no net change occurring. In essence, Gibbs free energy is a measure of the energy available to do useful work in a system. It helps in predicting the direction of chemical reactions and phase transitions. Gibbs free energy is named after Josiah Willard Gibbs, a famous American scientist. He is credited with much of the development of chemical thermodynamics, and he proposed a thermodynamic concept to simultaneously combine the concepts of entropy and enthalpy. He called this concept free energy, which is now called Gibbs free energy in his honor and is given the simple symbol capital letter G. Free energy is energy that is available to do work. However, not all free energy available for work is used efficiently. Living things are some of the most efficient users of free energy, although most are not even 70% efficient. The energy released in a spontaneous reaction is available to do work, and this energy is called Gibbs free energy. The change in Gibbs free energy, denoted by the symbol of delta G, is the maximum amount of energy that can be coupled to another process to do useful work. The change in this energy is related to the change in entropy and change of enthalpy of the system. Temperature in the equation is in Kelvin. All spontaneous processes release free energy and they are exergonic. In contrast, non-spontaneous processes are endergonic. To predict the sign of delta G, or the Gibbs free energy, we should consider both enthalpy and entropy. We have here the table 6.2, or the factors affecting the sign of delta G or the Gibbs free energy. In the relationship of Gibbs free energy is equivalent to enthalpy minus temperature multiplied to the entropy. On the case 1, if the enthalpy is negative, the entropy is positive and the Gibbs free energy is negative, the result would be spontaneous at all temperatures. In the case 2, if the enthalpy, entropy, and the Gibbs free energy is all negative, the result would be spontaneous towards low temperature. Also, if the enthalpy is negative, and the entropy is also negative and the Gibbs free energy is positive, the result would be non-spontaneous toward high temperatures. In the case 3, if the enthalpy, entropy, and Gibbs free energy are all positive, the result would be non-spontaneous toward low temperature. If the enthalpy and the entropy is positive and the Gibbs free energy is negative, the result would be spontaneous toward high temperature. In the case 4, if the enthalpy is positive, the entropy is negative, and the Gibbs free energy is positive, the result will be non-spontaneous at all temperatures. Predict which of the four cases in the shown table will apply to the following. For the problem A, the reaction is exothermic. The change in enthalpy is negative. 12 moles of gaseous products replace 7 moles of gaseous reactant, and the change in entropy is positive. The reaction is spontaneous at all temperatures, which makes it similar to the case 1. For the problem B, the reaction is endothermic. The change in enthalpy is positive. 1 mole of gaseous reactant produces 2 moles of gaseous products, and the change in entropy is positive. We expect the reaction to be spontaneous at high temperatures and non-spontaneous at low temperatures, which makes it similar to the case 3. For a reaction carried out under standard conditions, the free energy change is called standard free energy change. We have here the table 6.3, which is the table conversion for standard states. For the state of matter, We have the gas with a standard state of 1 atm, liquid for pure liquid, solid for pure solid, elements for the change in Gibbs free energy degree reaction is equals to 0. And for the solution, we have the standard state of 1 molar concentration. In general, the change in Gibbs free energy degree of reaction is equivalent to the summation of stoichiometric coefficient multiplied to the standard free energy of products minus the summation of stoichiometric coefficient multiplied to the standard free energy of reactants. Calculate the standard free energy change for the reaction at 25 degrees Celsius. We have here the given, which is the change of standard free energy of MgO, which is equivalent to negative 569.3, C subscript 2 H subscript 2, which is equivalent to 209.2, CO subscript 2, which is equivalent to negative 394.4, and H subscript 2 O, which is equivalent to negative 237.1. For the problem A, the change in standard free energy degree of reaction is equivalent to 2 change in standard free energy of Mg or magnesium plus the standard free energy degree of oxygen subscript 2 minus the 2 standard free energy change of MgO or magnesium oxide. Next, substitute the given values to the given formula. Now we have the 2 mole multiplied to 0 plus 1 mole multiplied to 0 minus 2 mole multiplied to negative 569.3 kilojoules per mole, which resulted to negative 1138.6 kilojoules. For problem 2, we have the standard free energy change of reaction is equivalent to 4 standard free energy change of CO subscript 2 plus 2 2 change in standard free energy of H subscript 2 O minus 2 change in standard free energy of C subscript 2 H subscript 2 plus 5 change in standard free energy degree of O subscript 2. Substitute the given values to the given formula. Now we have 4 mole minus negative ay, now we have 4 mole multiplied to negative 394.4 kilojoules per mole plus 2 mole multiplied to negative 237.1 kilojoules per mole minus 2 mole multiplied to 209.2 kilojoules per mole plus 5 mole multiplied to 0, which resulted to negative 2470.2 kilojoules.